another minute. Mm, okay, we are recording here. It's not really important. It will record over here. Let me open the chat. Good. And let's start. Um, before a few people ask about solutions for various homeworks. I think that the one that I actually prefer you to send videos with solutions are the question with the train track or the train switch that ask how I can use a train switch as so. Can I get the distance a bit better? Distance to a distance. So, oh, this experiment, too much blur. Okay, we need a different background, or which will be easily obtainable by creating a virtual train track, train switch. Here is my train switch. Here are my my trains that are coming in some arbitrary order, say 1, 2, 3, 4 are sorted in decreasing order or decreasing from the direction of the junction. This junction refers to the last question in homework 1, which involved train switches. And I want to ask how can I merge them in n log n something. And n log n definitely can refer to something different. We talked about model of complexity where what I measure are not necessarily running time, but something that could be much more bottleneck wise, much more important than direct running time. For example, number of accesses to hard drive, because hard drive is very slow to access. SSD are faster, but still much slower than main memory. So I want to minimize how many time I'm performing access to the memory. In this case, I was limiting the time that a trained track named 1, 2, 3, 4 can access the memory, and was asking, can I sort the whole thing where every car will pass through this junction, through the switch, only log n time, and what's the argument, of course. And so let's say that they are arriving in order 1, 2, 3, 4, and I want to sort them in order 4, 3, 2, 1. I want them to appear, but in reverse order, and I'm just doing merge sort by separate them arbitrarily. I'll separate this part over here, then I'll separate this part over here, and now I want to create what did we say? I want to create a sorting at which each pairs of tracks will be sorted. Just as merge sort, where the first thing in the wheel algorithm after I separate into pairs is make them all sorted in the correct order. That is, now I want, so I'll ask, hey, 4, are you smaller or larger than a 3? And we won't say 2 is smaller than 4. That's why, and since we want the order to be reversed, I'll create one pair over this way, create a pair over the 4 and 3 that you can, 4, so is a 1 and 3 that you can see over here. 1 is smaller, that's why 4. Compare 3. Now I have each pair sorted, separate one pair to the left, separate one pair to the right, and now I have a list of length 2 to the I in the top, 2 to the I at the bottom, and I want to merge them, which I can easily do by just the merge algorithm. Had I have more cars, they would just wait for me either on the left side or on the right side, either on the left side or the right side of the whole picture. So in this case, I would merge them by comparing the minimum of the set that sits on this side, the minimum of the set that the minimum of the sets that sits on this side. Again, compare the minimum of the set that sits on this side, the minimum of the set that sits on this side. In this case, it could be the minimum of this set must be 1, minimum of the set must be 2. 1 goes first, 2 comes, now I'm comparing 2 to 3, 2 is smaller, 2 will come, 3 will come, and 4 will come, and indeed I succeeded by just log 4 iterations, log passes per steps. What's the argument of the running time would be that every track by itself finds itself inside a length of a run, where this run is sorted, and of length is sorted, and is length 2 to the I for some number I. So maybe one of the next homework I'll ask similar question, just send me videos of how you solve the case of using again a trained switch, solve the use this time quick sort rather than merge sort with the same mechanism. Okay, any other questions about homework 1? Hi everybody, by the way, thanks for being so patient when I was, if anybody interested in discussion of is COVID just a flu is good relationship or not, I have very strong opinion, but outside of the scope of this course, questions about homework 1 that you want me to address? Uh, Mistakes that I saw in homework 1 that were typical, remember it for the midterm, some mistakes that were happened frequently in question 3 in homework 1. I was homework 1 question 3. I asked about a value s, let's call it s sub I, which was 1 plus 2 plus 4 plus dot dot 2 to the I. The last element si was this sum, which was, of course, for the purpose of giving you time to practice geometric sums, one of the many times. That's, by the way, one of the very few times where I actually care about what is the upper bound of the sum. And this number, the upper bound of the sum, 2 to the I, the last element. So this number you had the formula at the end, you had the formula at the top of the homework. This you had the formula at the top of this homework. This number is just a 2 to the I plus 1 minus 1 divided by 2 to the I, 2 to the 0, known as 2 minus 1. So that's divided by 1. Let's just call it 2 to the I. And this sum could have run as long as this number is small or equal than n. From which case you're ignoring the 1 and saying that's why the maximum number of iteration will happen by taking log 2 from both sides. I can argue now that by taking log 2 from both sides, I will next argue that log 2 of 2 to the I plus 1, log 2 of 2 to the I plus 1, that's why we'll keep running as long as this number is small or equal than n. Log 2 of 2 to the I plus 1, what happened to the I plus 1? The I plus 1 is moving to the top. So I plus 1 times log 2 of times log 2 of 2, the I plus 1 move to here. What is log 2 of 2? This is just 1. So I plus 1 should be smaller or equal than n, implying that the number of iteration will not be more than log n. So that was clear. I saw quite a few mistakes about this part. So just to correct, in that refers to question 3. In question 2, on the other hand, guys that watch on Twitch, if there are any, I don't see the chat of Twitch. So if you have questions, please post them via Zoom. But I realized it's very last moment, and with COVID, it was very unclear if I will or if we don't have everybody today. Question 2, people got correctly to the idea that we had some number si, which was increased by 1 at each, it increased by I at each iteration, 1 plus 2 plus 3 plus 4 plus all the way up to I. At this point, you went to the top of the homework to see the formula for this creature, which is I plus 1 divided by 2, which will, if you want to call it I squared divided by 2, I squared divided by 2, that's close enough, or just I squared, and you ran this sum only as long as this number is smaller than n. And now I saw to people that from this point they concluded that the running time is therefore t of n is therefore theta of n squared. which was exactly the opposite, the reverse. The intuition of something needs to have a quadratic behavior is correct. It is a quadratic, it behaves like I square, but it's not, the running time is not theta of n square, it is instead theta of square root n. That's because you can only have square root n many iterations until the sum is start to become larger than n. So that was mistakes that I saw in quite a few homeworks. Amir, typical mistakes that you saw in homework 1? Okay, sure. Sure. The dynamic array that was there, it might. Maybe I'll ask in the homework again, question of the dynamic array. We take an array and multiply it by 1 plus alpha, multiply by 1 plus alpha every time that it becomes full. Now, if I want to keep it, to combine it with open addressing. In open addressing, as we discussed last week, in open addressing, I'd like to keep m, the number of elements in the array, smaller or equal than 2n. M is smaller than 2n, which would mean that I'll take an array of size m and start inserting element into it, and once the array is not 100% full, but the array is more than 50% full, m always in hashing the number of cells and the number of keys. The moment that m is more than 50% full, then I'll allocate an array twice as large and perform a rehash. And that's actually a very typical usage of dynamic array. And I can replace the array of size. Now, it will not necessarily be 4n. I mean, I'd like it to be, I can double the size of the hashing, or I can increase it by a factor of 1 plus alpha times the old value, the previous value of m. What is alpha here? Just as in the homework, it's some tunable parameter. You can say, I want to perform fewer rehashing. I want to have fewer rehashing, and I'm not particularly short on memory, so I value more computer running time versus memory. So I'll take alpha to be large, maybe create much larger array, or I value memory more than time. Why do I value memory more than time? It's not because you don't care about time, but because maybe this hash table is one of many other hash tables that are all competing and using the same memory, and once you overshoot with one of the arrays, then you start to run into caching issues which slow your program dramatically. So you really want to go you want to squeeze everything into your main memory of 8 gigs or whatever, and yeah, that's how it will go. Okay, very good. I think that's as far as the tricky part of homework 1. Homework 2, I'll assume that everybody by now submitted. Questions about it, about homework 2? Yeah, okay. Well, then it would be nice if they would join us now, and from the students which are alive with us, are there any questions about homework 2? Okay. A question that is maybe was from our homework 2, one question that I don't mind chatting about was a question about storing low versus low versus low. We want to consider all these items are identical, which doesn't mean that we don't want necessarily to store the different shapes of hello as maybe auxiliary data, but we want, once we are doing a search with this hello, we want to find hello even if it's written with large letter. That was question 2, what I refer to as the question that was the hint for a few questions both in homework 2 and in homework 3. So we still might want to report different hellos, but the key is not auxiliary data. In the auxiliary data is what we can, in the auxiliary data, we are writing the student grades, the student address. As a key, we will use the student ID. So at this point, we want to say, let's make sure that the key is the same. So the way we solve problem of this form will be to define the canonical form of a word. I mean, canonical form of a word, a canonical form of a key. What is a canonical form is whatever you want to define as a canonical form. But it means that, so why do I introduce this term of canonical form that I found very useful, is it means that when before inserting each one of these words, I will not insert this word directly, but I'll insert the canonical shape or convert it to its canonical form of this word. For example, in this very trivial example, I'll decide that the canonical form, that the canonical form of the word hello would always be hello written with small letters. Let's see. I'll always decide that the canonical form of a word will be write this word but use capital letters. Or decide that canonical form of a word is always using small letters. Or decide that you'll alternate between the letters. It's entirely up to you. How do you define the canonical form? But once you decide about it, you must be consistent and persistent with this. Every time that you'll see this word as a key, you'll transform it to its canonical form, which means that you can store the key, the word multiple times, but the key will always be the same, will be the canonical form of this word. So use say capital letter, then when you see any one of these words, you will convert it to the canonical form and insert it if it's a fair insertion. When you are searching for, no matter which one of these words you are searching for, you will perform a canonical form conversion and search for it. Okay, and I'm sure that you all figured it out, just didn't use this very fancy, pretentious term of calling it canonical form necessarily. Why do I insist on this fancy term canonical form because I think that it's helpful in other homeworks like homework 3, where you had the tic-tac-toe. You had X or 0 or O or nothing, which we can represent as the value 1 or 2 or 0, depending whether it's X or O or null per the cell. And this will be representation only of this cell. I'll use one of these three numbers, 1 or 0 or 2, to denote whether it's X or etc. Okay, next I have 9 cells, or in a K by K game, we have vector of length K square. Right. And even if you don't like geometry, the term K, the term vector here just means it's a list of numbers. It's not a single number, it's a list of it's a list of numbers, sorry, which will come from this cell. So that would be cell 1, cell 2, 3, 4, 5, 6, 7, 8, 9. A list of K square cell if the game is K by K. And each number is one of these values. And you're just looking at this long vector and apply dot product on it. Apply the dot product on this number. Sigma of AI xi. Xi will be one of these digits. You can also combine them into larger digits if you want, but that would be fine. All of it mod m, and sigma xi ai will be, of course, will give you the result. Will give you a value of one configuration. Say of the configuration x, 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 it will give me some value of this hash function. And I can go ahead and store or search immediately for this configuration, but I can also look at this value, which is just a number, and say, hey, if I rotate it, because if I rotate it by 90 degrees, it's identical configuration. Again, if I don't think about this configuration, but think about this configuration obtained from this by rotating by 90 degrees, this is a different configuration. When I'll write it as a vector, I'll get a different number over here, which I could. And presumably one of this number will be different than the other. The value will be different when I look at this. It's a hash function of this number. The same if I'll do a flipping rotation. So I have 8 values that I can get based on all the rotation by 90 degrees, and rotations and flipping, mirror symmetric flipping. Each one gives me a different value. Now it's my time to decide what is a canonical form out of all these values. I can decide that the canonical form of a configuration would be, out of all the translation and rotation, the one that says, gives me the minimum value. For example, that will be the one with the canonical form, or the one that is lexicographically the smallest, or anything else that will be unique and we'll say out of the whole all 8 configuration will bring me always to the same value. That is, I look for the value that is the smallest, and that's the only form that I'll store. So from these 2 examples, will I store this configuration or this configuration? I don't know. The one that gives me this sum, the one that brings the hash function to a smaller value. That's the one that I store. And if you'll ask me to perform a search, in the whole database and search for one of the configuration. I'll first say I don't necessarily want to look at this configuration. I want to look at the canonical form of this configuration, which might happen, which I can easily compute before the search. Can easily compute what is canonical form by computing just a hash value and look at all 8 configurations. So that's the whole idea of canonical form. So that's worth mentioning because you also need things like it in homework 3. I'll talk more about homework 2, happily, but either in office hours or it will wait for Monday where we'll have more people joining us, since I think this time was very, very unplanned, and they are according to my viruses. Questions? Anything? Okay. Okay, let's. What are we believing, or what do I need you to read at the meantime? Is make sure that you understand. Let's write the things that I expect you to know from the lecture that I posted in the end of the last lecture. We finished Dijkstra, including the version of that uses the pi values. The pi version that uses the pi values appeared as one of the homework questions, but you can also find it in the textbook. We talked about we talked at the end of the class, we talked about the time analysis of Dijkstra, only at the case where it uses binary heap. Using binary heap, each decrease key operation, the decrease key operation, and extract mean operation. Each one of these operations are doable in order log n. And now when you are looking at the code of Dijkstra, you're reaching a vertex u at the graph. You just made it into the set capital S. You look at every edge u v, assuming that v is not in S, and you tell v, hey, d of v. D of v is my estimated cost of any path that reaches v itself. Here is a different path that reaches v. U tells v, if you'll use the edge that connects us, then the cost of reaching to v will be d of u, how much it costs to reach u, plus wuv, the cost of this edge. This would be always wuv. We always denote wuv to denote the cost of the input edge of each one of the edges, wuv. And d of v might say, no, the vertex v might say, yes, it's a good deal, I'll take you on it, and will, in this case, d of v will decrease. That's the operation decrease key. And d of v will decrease. D of v always starts from infinity, like every vertex that is not S, and d of v always ends at the delta of v, the distance to v itself. However, along the time, what happens to DOV is either stays the same or goes down. Stays the same or goes down. Depending on DOV will change its value only of if DOV, the previous DOV, sorry, the previous VOV is larger than the offer that U offers to V, and in this case the new DOV, so this is if this condition holds, then DOV equals D of U plus W U V. But that happens only if this is cheaper than this itself. And in this case, we are performing the decrease key operation. How many times are we going to perform the decrease key operation per edge? At most twice. Once when I reach this edge from U to V, and once when I reach this edge from V to U. So each such operation takes log n. So overall, the decrease key operation, I'm spending m. M always a number of edges. M is a number of edges, always. M times log n. So that's one component of Dijkstra. And the other component of Dijkstra was that sometimes we perform extract mean operation from the heap. A vertex is added to the heap only once, is removed from the heap only once. So this will take n, because n, the number of vertices, times log n, because that's the time for insert or delete from the heap. So which is n log n. So the overall running time is m log n plus n log n. M plus n log n. And that is nice. Is this optimal? Not really. But practically it's optimal. As a recommendation, that's optimal. There is a data structure that is significantly more complicated than heaps, and to confuse, it's called Fibonacci heaps. I'm pretty sure that that's not how you spell Fibonacci, but it's pretty close enough. Fibonacci heaps. These are not binary heaps. Fibonacci heaps, which are not binary heaps. What's the difference between Fibonacci heaps versus binary heaps? In Fibonacci heaps, extract mean still costs log n. Extract mean still takes log n, so we are spending n log n for the extract means operation, removing a vertex at each moment and adding it to S. However, the operation of decrease key doesn't cost log n anymore, but in the Fibonacci heaps, decrease key only cost a constant time. On its amortized analysis, a bit harder, but on average, each decrease key will cost only constant time, which now implies that you can perform the whole Dijkstra algorithm will take n log n plus m. That's with Fibonacci heaps, and with binary heaps, the running time will be order of n plus m log n. So see the difference. Look at the m at both expression. Here m is not with Fibonacci heaps. M the number of edges is multiplied by 1. With binary heaps, that I suggested as a more practical data structure, you're getting m is multiplied by log n. So why am I? So we're putting theory in the right place, as it's nice that you can do it asymptotically better, but in practice the binary heaps are working just as well. And actually, in many cases, your best gamble is not to use fancy data structure at all and just use an array for every vertex or matrix that will have a cell for every pair of vertices. And then each operation takes, if you are just using an array for each operation, then each one of these two operations, if you're just using arrays, will be take theta of n not less than n, theta of n not, theta, remember, not less than n, not more than n, order up to constant. It's both order of n and omega of n. You're just using an array and finding who is the smallest value, or just decreasing this value. Decrease key actually costs a constant time in this case, but finding the minimum or deleting the minimum takes linear time, and then the whole Dijkstra takes order of n squared, but with much nicer constants, as quick as you can get. So that's maybe the best algorithm if your graph is dense. That is, m, the number of edges, is close to n, is close to n squared. That is, every vertex has a lots and lots of neighbors. So you have to finish Dijkstra. You have to also finish BFS. All of you know BFS, but BFS that uses queues. To see BFS as just a simple case of Dijkstra. This is a bit, notice the order. So BFS is a special case of Dijkstra because I did use BFS also to explain Dijkstra, but now I'm going the opposite way. I'm saying if all the edges have cost of 1, then BFS becomes just a special case of Dijkstra, and then maybe I don't need binary heap. I can use with just a queue, store all the vertices in a queue, and perform the operation of nq or dq, remove a vertex from the top of the queue or the bottom, or from the top of the queue, and insert a vertex to the tail of the queue, and then each operation costs linear time, and the running time of the whole BFS is order of n plus n, is only n m plus n, which is optimal because that's the time that it costs me to read the graph as good as I can get, because I'm essentially running Dijkstra, but I notice that the cost of every edge, w u v, is always 1, so I don't really need the binary heap. I can use the queue. And please cover it. I found it very counterintuitive. Maybe it's only me, but I found it. Saw it originally, and until I spent time convincing myself, I found it quite counterintuitive. That's why the order of visiting the vertices is exactly the same as Dijkstra, but I don't visit. I don't miss vertices. Convince yourself that Dijkstra works. The proof of Dijkstra that is that When Dijkstra ends, it reports for every vertex some number d of v. It reports for some number for every vertex v, some number d of v. Now, it's easy to convince ourselves that as the algorithm runs, d of v is always larger than delta from S to V. Delta of S to V is the length of shortest path. And D of V, quite easy to convince yourself, is the length of a path to P. Length of a path. Not necessarily the shortest one, so it's quite obvious that the optimum, the shortest path from S to V, is better, is smaller than the length. That it's easy to convince ourselves that the length of a path is better than the length of the shortest path always as the algorithm progresses, but a bit harder to convince ourselves. So please go over the slides to see that when the algorithm terminates, we are also sure that d of v is also not small, not larger than delta. These are implying that they must be equal, implying that d of v is actually the length of the shortest path. It takes some time, you need induction for it, induction on who, what, if there is a vertex that is lying, where this vertex will be, and you are doing some search, and needs to prove it. Not entirely trivial, check the slides. Okay, so that's summarized a Dijkstra and summarized BFS. Next, I posted a lecture now hosted at this moment on Twitch that gives you a Bellman-Ford, what to do with graph with negative weights. Or Bellman-Ford is actually much more rigorous algorithm than Dijkstra. Dijkstra is very fragile about the condition that it can work. It says, I want to perform, Dijkstra says, I'm looking at this edge u, v, and I have values which are the estimated distance from S to AU. I have some estimated distance from S to V, d of V, and I can look at this edge, especially if it has a direction, and perform the relax operation. The relax of uv. If dv is larger than du plus w uv, then dv equals du plus w uv. That's a relaxed operation across the edge uv, and Dijkstra tries to say, I want to be very aristocratic about how many times I'm going to perform this relax operation for this edge. How do I do it? It's fine to do it only once, but for this, to perform this relax operation for this edge only once, when I perform this operation, I must be sure that d of u, this number that you see over here, d of u, the estimated distance to u, is already as low as it can get. That is, d of u that I'll have to compute will have to be already in its lowest value, that is, the true distance to u, and only then I'll perform the relax operation, and in this case I can do it only once. And that's some luxury that you can enjoy only if the graph is very well structured and no surprises. What type of surprises could there be? It could be that you'll have negative edges, and then what you thought that d of u is actually the shortest path, it turns out to be that there is an edge that somehow influenced the distance to you and you didn't notice this edge. And later on you see that d of u has decreased again. So it makes a Dijkstra very faster, but it also makes it very fragile to all the edges must be strictly positive, or at least equals to large or equal to 0. What about if I'm not sure about positivity of the edges, or actually a much more robust way? I mean, I can tell you about other applications of that we saw of a of Bellman-Ford-like algorithm, so that you can perform this. You can pick this edge once in a while and say, hey, will you benefit from doing the relax operation? And later on, maybe d of u has changed. Are you benefiting from performing the relax operation once again? And I'll do it just every once in a while until I'll see that everything's stabilized. No weights are changing in the graph no matter what. D of v of all the edges are all changing no matter what, and I cannot do a successful relax operation nowhere in the graph, and that would be my sign to stop the algorithm. So Bellman-Ford is way more rigorous, and you can throw on it many more complication, we'll talk about them next week, that you wouldn't suffer for a Dijkstra. That will cause Dijkstra to scream paranoidally. Don't do it. So but what's the cost? That you need to perform the relax operation for the same edge multiple times. So do convince yourself about Bellman-Ford, and mostly, and I have this fight every time that I'm teaching 445, the proof is very much constructive. The proof is an algorithm by itself, if you wish, and it tells you a lot about what happened in the algorithm and what happened in the graph, and mostly the proof tells you how to improve the algorithm in various cases. Some I'll ask in the homework, some I'll ask in the midterm. Make sure that you understand the proof of correctness of Bellman-Ford. I'll put it in much higher priorities than the understanding the proof of most other algorithms, because in Bellman-Ford, as opposed to, for example, the proof of Dijkstra, that is more constructive. It's more proof by contradiction. Sorry, it says assume that the Dijkstra lies, then something bad happens and something that cannot happen will happen, and there is some induction involved here. But it doesn't tell you immediately how to improve aspects of the algorithm, while the proof of Bellman-Ford is really essential for understanding what's going on. Okay, we'll talk if students will have more questions about homework 2. Nothing in the chat, nothing in the okay, Greg, you had various questions in the email. I hope that you are feeling better than me. I also had, yeah. Gang, do you have more questions? Okay, if you need more pointers for health services, including you want to get this antiviral medication. Let's speak about it offline. Okay, there is a big topic of multi-criteria shortest path that I'll get back to, but in the meantime, I want to start with dynamic programming. Dynamic programming is a big topic. We'll see about 6-7 algorithms that are all related to dynamic programming, and it's a very general method, how would I say, to solve problems. And actually we have seen a few examples so far, as it relies on several principles that essentially said if you can take the solution to a big problem and the solution to the, where is my camera? If you can take the solution to a big problem and your solution from a big problem consists of solutions, optimal solution, to smaller problems, then it has a good chance to be discoverable via dynamic programming. What do I mean? It's not always true that the solution to the big problem consists of solution to sub-problems. Maybe it's true, but there is many cases that I have no way to look for solution to smaller problems. If I ask you to guess what is the solution to a key lock combination, I have a bicycle key lock combination and I have numbers and I want to play with them, then even if the solution is, of course, variable code 1, 2, 3, 4, 5, that is a solution to my kilo combination, and I guessed correctly the 1, 2, I have no way to know if that's a correct solution or not to any sub-problem until I'll solve the remaining larger problem. So that's not a solution that I can decompose into smaller problems. For dynamic programming, I can always take this problem and discover it via discovering solution to sub-problems. And we already saw a few examples of this case. For example, let's talk about Dijkstra. Dijkstra says I need to ask what is the shortest path from S to T. That's my big problem. What's my shortest path from S to T? And what will you say about Dijkstra? Look at V5 over here, vertex 5 over here. As a rule, I don't know if the shortest path from S to T goes through V5 or not. Looking at a vertex, I don't know if the shortest path will use this vertex along the way or not. I want to know what is the shortest path from S to T. What's the importance of V5? Well, I'll tell you what's the importance of V5. I don't know if the solution will work, if the shortest path will use V5, but I'll still, nevertheless, will compute D of V5, which would be the distance from S to V5. Why? Because if the solution to the from S to T go through V5, then the shortest path from S to T will use a portion of it. Portion of this path will be the shortest path from S to V5. So, am I sure that V5 will be along the shortest path? No. But I'll compute for V5, and so I'll compute also to V4, and compute for V3, and for each other vertex, I'll compute the shortest path to them, because if they are very close, much closer to S, then they are, and the shortest path must go through some vertices, and whichever vertices they are that are along the shortest path, even though they are just intermediate vertex along the shortest path from S to T, even though they are just a middle station, the path to them is part of the overall path from S to T, is a solution to the big problem of the shortest path from S to T. So it really helps me to know what is the shortest path to each and every individual vertex along the way. So that already shows you the mindset for dynamic programming. Okay, let's start with our set of problems for dynamic programming. And the first one is a problem about strings. And strings, sequence of letters, and looking at a string sequence of characters, X like A, B, C, A, and I want to define what is a subsequence of X. Well, and it's really sorry for the being very uptight with the definition. It's very formal definition. A subsequence of X is any sequence of characters that is obtained by taking X, and you can delete from X any characters that you want. What you're not allowed is to switch the order of any two characters. It is take from A, B, C, A any characters that you want, including null at all, and you can delete a character, but don't change the order of any characters that you didn't delete. Otherwise, it will not be a subsequence anymore, just a formal definition. That is, I can take A, B, C, A, delete the last A, and be left with A, B, C, or take A, B, C, A, and delete the B. Here I'll delete the first B and the first B and the first C, left with A and A only. Remember, it's not a set, it's not a collection of items, it's a sequence AA. It's not a single A. Of course, I can delete each one of them and then A. Or I can delete none at all and be left with A, B, C, A. That's what a sequence, that's what a subsequence of a string is. Next, let's define what is a prefix of X. First note, a good reason that the algorithm that I'm going to describe is confusing from first look is that it has lots of indices, so let's start getting used to it at the very beginning. A prefix of X is a string. A prefix of X, I'll always denote it as X square parentheses 1 dot dot till some number M is the sequence of the first M characters of X. You must decide about what is M. In this case, M can be 0, 1, or 2, or 3, or 4. And once you decided what is M, you must take, without changing the order, the first M characters of X. So X1 dot dot 4 is the first 4 character of X. X from 1 dot dot 3, the first 3 characters. X1 dot dot 2, the first 2 characters. X from 1 dot dot 1 is just the first A that you saw over here. And X from 1 dot dot 0, remember it, it's the empty string. This is just the empty string. Okay, this will be the prefix. We'll also have suffixes defined analogously, but we'll wait for later in the course. So that is what a prefix. Okay, now I can define what is the longest common subsequence. And in this part, this definition is, by the way, taken from the textbook, the CLRS. So the longest common subsequence LCS problem is the following. I told you about one string x1 dot dot m, all the string, one long string of m characters, another string y, n containing n characters, and I can define a lot of subsequence between them, right? I can say let's say that x equals a, b, c, d, e, how many subsequences can I create? Help. How many different subsequences can I create? Anthony, Gang, Air, Rachel, Christopher. The number is large enough so you don't have time to compute it, to compute all of them directly, uh, but you can. It's still very easy to give me the correct number. Anybody? You're on the right track. I Okay, I need to decide, but the order at which I delete them doesn't matter. What you're describing exactly is how many permutations do I have, which is in the right way, but I need to decide if I'm going to delete the A. So possibly let's maybe put a guillotine next to the A. Maybe that will be a good description of need to decide if the A is going to arrive or going to be deleted. And that's a decision that is independent of whom I'm going to delete or not delete later. So I'll just denote it by a flag 0 or 1. So that's a hint. And that's a decision that I'm making for the A, and that's independent of what I'm doing for other characters. What? I need to tell you about the A, deleted or not deleted, 0 or 1. Similarly for the B, x2, similarly for the C, deleted or not deleted. Altogether, you have a combination that will look like, if I'll say 1, 1, 0, 1, 1, will, let's understand it as don't delete, don't delete, delete, so don't take the C, and don't delete, don't delete. So only the C was deleted because of the 0 over here, so the sequence that I'll generate is actually A, B, D, and E. C is missing. So how many subsequence can I generate? Well, 2 to the length of x, if x is of length m, that is 2 to the m many subsequence, because each such subsequence is generated by just keeping a flag for each character. Do delete it or don't delete it. And I do call two sequences, I'll think about them differently if they came from different character. There is a bit confusion, possible confusion here. For this sequence, I'll still think that the number of subsequence of this is 2 to the 3, which is 8. Because I still think about A1, A2, and A3, I still think about them as different characters. That's a bit, you'll see the applications and you'll see why. Even though they are the same character, I'll still distinguish between them. So still the number of subsequence over here is the same, 2 to the 8. But if my vector that I showed earlier was 1, 1, 1, then I'll I don't delete anybody. If my vectors that I showed earlier is 0, 0, 0, then I delete everything, creating the empty subsequence. Back to the LCS. So there are a lot of subsequences of X. There are a lot of subsequences of Y. My first question is find a subsequence that is common, both a subsequence that is both a subsequence of X, but at the same time subsequence of Y. And your answer will be, oh, it's very easy. Take the empty subsequence. It's always a common subsequence. That's why I'll ask, find the longest common subsequence of both X and Y. Okay, so that's the LCS problems. When is related? Here is X is a set of functions that both Anthony and me were working last night about on the same file. I added some pieces of code. Anthony added some pieces of code. See that Rachel was also answering in the text. Yes, it's not 5 factorial, it's 2 to the 5. But yeah, I guess, yeah. So Anthony and me were working on we got from Git the same file. We were working on it and simultaneously, and each one of us added some models to the file, and now we want to merge it. And our first merge is to see what is common in both our files versus what are the pieces that only I added or the pieces that only Anthony added from yesterday. And LCS is a good way to think about it, to see what is the most common thing that appears in both these files. Assuming that we didn't change the order, we just inserted pieces or possibly deleted pieces. I want to know how much of these files are similar to each other, so we can easily do the diff files. What appears only on my side but not in Anthony's side, and vice versa. Or you can think about two sequences of DNAs. Each was started from the same source, but each one went through a different sequence of mutations. And you want to ask, what is the commonality of both these sequences? Or you can ask, is the sequence A is more similar to Y comparing to the similarity between X and Z? And the LCS will say the more similar it is, the longer the distance is. We will see, by the way, a very, very important notion, a very close relative of it, of the LCS, is the edit distance, which is somehow more sensitive to what is different between the files versus LCS that says what is common between the files. It's a bit more weight about what is common versus a bit more weight about what is the distance. Okay, so LCS, hopefully it defines 1 over all the exponentially many sequences of X, exponentially many sequences of Y, and find only subsequences that are common to both, and tell me what is a longest one, the one that has maximum number of characters. And when I'll talk about the LCS, I'll talk about a longest one, not necessarily the longest one. It could possibly the answer is not unique. Possibly there is a lot of subsequents all with the same length. For several years, pre-corona time, there was we had a very in CS445, because of the way that I like to explain LCS, and it became somehow a tradition, which I did not create, to talk about CS445 salute, which looks like this. CS445 salutes. This gestures is they became somehow how students and the TAs and students were greeting each other by making this gesture, and was disqualified in Bajaj, if you wish, of and let's see why did I come to it. This is a drawing that I picked from a student's exam in CS445. The student performing a salute, what he said is 445. And why is it? Let's think about the string x that I write here horizontally and the string y that I write horizontally as well. And I like geometric problems, so I'll think about the LCS, longest common string subsequence, in the following way. If I'll decide to use a from here in the LCS, it will match to some a that appears in y. And I can draw this matching by drawing a segment between them. Similarly, this b will match this b. I can draw a segment between them. Same for between this C and this C, but the same between this B and this B again. By the way, a possible LCS of XY in this example will be indeed BCBA, right? BCBA is a subsequence both of X and of Y. It has 4 characters, the length is 4, and you'll figure out that it is indeed, you cannot find an LCS of length 5 in this example out there. But now let's think about these segments that I just drew. So these segments connect the same letter of X to the same letter of Y, and I need to choose what are the segments that I'm connecting. A letter, a character, can be matched only to a single character of the other side. And let's draw a quick example. Let X be AB and Y be BA. I want to do it again. X is AB and Y equals BA. And can somebody please tell me what is the length of the LCS of this problem? What is the longest common subsequence that you can generate in this problem? The length of 1. I can remember a subsequence has the order implicit in it. I cannot change the order. So I can match the B to the B, but then I cannot match the A to the A. Or I can match the A to the A, but then I cannot match the B to the B. Definitely the LCS is not AB because it has a different order than BA. So the length of the LCS of X and Y is 1. And of course, let's have one more example. X will be A, B, A, and Y will be B, A, A. And in this case, what's the length of the LCS? In this case, it will be 2. Right? Again, think about our segments. I can match this A to this A, and now I have 2 other options. Either match these 2 A's, so one possible solution would be AA. A different solution is match the B's to the B's, so it will be B, but still use A. Okay, so you see where the salute came from, the CS445 salute came from. Place as many segments, if you like the geometric interpretation, write the two sequences and now place as many segments as you could, but two segments cannot cross each other because crossing will mean that the order of this side is different than the order of this side, that you need to reverse the order of these two. So that's an extremely important, useful problem. Indeed. Thanks, Rachel. Just I see your solution now. So LCS is extremely important problem. It's algorithm that is implemented if you go to your editor and ask to compare files. Good chance that that's what you'll get. If you'll go to Linux, Unix, and type diff, diff, is a command that is with some 1960s graphics, will show you the difference between two files. And of course, we don't like exponential algorithm. Let's start paving our way to solve this problem differently. Okay. Once again, of course, salute once again. And let's think about brute force our way into LCS. But I'll have more office hours this week, and as usual, by appointment, because of the time that I was sick. So we can have something at the evening today. Will probably work fine if people need. Okay. Checking every subsequence of X, whether it is a subsequence of Y. How much time do you need for it? Well, you can do it, the number of subsequence of X, we talked about it, 2 to the M subsequence of X. Now, if I'll show you something that is a subsequence of X, to check if it's also a subsequence of Y, you'll have it in the homework, but you can do it in linear time, actually. Once I gave you a subsequence of X and asking, hey, is this also a subsequence of Y? Yes or no, that you can do much more efficiently. That takes only linear time, but it still gives us overall exponential running time, one of the sequences. So we hope to do something better. And to get into a better algorithm, we first do the same mental tricks that we did in the case of Dijkstra. Dijkstra is looking for shortest path, but if one vertex needs to tell another vertex about a path that leads to it, it needs to do, say, the path that we are talking about consists of this vertex and this vertex and this vertex and this vertex, and there is a lot of information when I'm describing the whole path as a set of driving instructions throughout which vertices do I have to go. That's not very convenient to compare or to trade between information, or to update. Instead, what Dijkstra did was talked all the time about the length of the path. The whole algorithm is first asking what is the length of the path from S to T, and only once I figure out the length of the path, I can pave my way and going backward, finding somehow what is a path itself. You can use pi values, but you actually get away with some more complexity without the pi's, but it all happens after the algorithm terminates. The same will happen for all the 6 problems of dynamic programming that we are going to discuss. We are going to say, I want to know what is the LCS as a sequence of characters, or pieces of file or pieces of DNA, but for the time being, I will not ask what is the LCS itself. I will ask what is the length of the longest common subsequence. How many characters are there along the longest common character, and I'll compute this number first. So from now on, and probably when I'll discuss it, I'll talk about the length of the LCS. And once I know this number, we'll see how it helps me to figure out what the characters that forms the LCS. So for time being, we are going to speak about the length of the LCS. Next, and sorry for more confusing notations, if I'm looking at a sequence of characters, S is a sequence of characters. When I write S with 2 bars on the length, it's a cardinality of S, is just how many characters there are in S. Okay, so if y equal BAA, then y with bars on the side is 3. Okay, so far not too confusing. Now here comes the really confusing part. From now on, I want to remind you what is a prefix of x. X from 1 dot dot y is a prefix of the first I characters of x. Y from 1 dot dot j is the first j characters of y. I want to tell you what is Cij. I'm going to define it. I'm going to compute it in the algorithm. Cij will be the length, how many characters there are, in the longest common subsequence of not x of y as a whole necessarily, but only take piece of x, only the first I characters of x, and only the first j characters of y. That's what Cij is. So let's take some examples, because it's really important that we'll understand this definition before we continue. X equal A, B, A, D, E, and Y equals F, A, B, D. And tell me, please, let's compute what is C of 0, 0. C of 0, 0, which, based on the assumption, I need to compute what is x of 1 dot dot 0. X of 1 dot 0 is a prefix that contains the first 0 characters of x. The first 0 characters of x. Similarly, y of 1 dot dot 0. Again, don't be confused by the 1 over here. It's not the first characters of y. It will start at the first characters, but you are progressing 0 characters. So that's also, so this is an empty string. This is an empty string. And how many characters can we match between two empty strings? Empty, so there is nothing to match. Oh, that shouldn't be too controversial. Let's take the first interesting case. I think C of 1, 3. What is C of 1, 3? I need to compute what is, in this case, x of 1 dot dot 3. I should have let you answer, but because of we are running out of time, I'll give myself x of 1 dot dot. What is a 1 over here? It tells me go to x and compute at x the prefix that starts at 1 and ends at 1. X is A, B, D, A. Take the prefix of only the first 1 characters of A. So that's A. What is the 3 over here represent? Takes y from 1 dot dot 3 would be, takes the first 3 characters of y, which are F, A, B. What is the length of the LCS between these two guys? Well, they have the A that matches. That's nice. That's as long as you can get with only 1 character, which would be A. What is therefore C of 4, 4? C of 4, 4 will mean takes everything, the whole 4 characters of X, takes the whole 4 characters of Y, and ask what is the LCS between these two guys. And if I'm not mistaken, the length of the LCS would be I can match the A to the A, the B to the B, the D to the D, so the answer should be 3. There are 3 K letters that I should match. So where are we going with this algorithm? That while we want to express, we have a big problem of very long X and very long Y. And the way we will get a solution to the larger problem of long X and long Y would start by computing LCS of very short sequences and then let them grow somehow. You don't know exactly how to let them grow, so you'll have multiple operations. It's multiple options. It's not a greedy algorithm. You will not always increase the LCS, but you will check various options, of starting from very short sequences and slowly let them grow. And at each time that the sequence growing, you will see whether you need to update the length of the best LCSs that you found so far. And since you would not like to work with the LCSs themselves, you'll see if you need to check the numbers that are stored as a CIJ. This length is of the length of the LCSs of from very short for X and Y. I have a window. I'm just looking at the prefix of 1 characters of X and 1 character of Y into I look at maybe 1 characters of X and 4 characters of Y. Or I'm looking at 2 characters of X and 2 characters of Y and ask between them, and so on, and slowly moving into longer and longer problems until eventually I'll get to CMN, which is just the LCS of the whole of X and the whole of Y. That's what they will tell the user as an output, will be the highlight of the algorithm. And we are going to compute this number by computing Cij for few and very, very elegant and very cute algorithm of smaller and smaller LCS. And by the way, I'm going to actually describe 4 algorithms, 2 that appears in the textbook and 2 that does not appear in the textbook. I'm going to describe LCS, which you can find in the textbook, in CLR. I'm going to define edit distance. Extremely important and useful algorithm. Every time that you are using iSpell and you see that your editor correct your spelling grammarly into something else, every time that you are talking to Siri or Alexa or somebody and it understands what you are saying, you are actually using various edit distance algorithm, because what you thought you typed might have a spelling mistake, but it was able to find a word that was very similar to the word that you typed, and you used edit distance for finding the most likely, the most reasonable word that you meant to write. I typed hello, and my speller understood that I meant hello without the W, because somehow the distance from this word to this word is much smaller than the distance from this word to, let's take a different word, CAT, and so the distance from hello to a cat is much larger than the distance from hello with a spelling mistake to hello without a spelling mistake. So the edit distance understood it. So we'll speak about edit distance, and we'll talk about fréchet, and we'll talk about fréchet and dynamic time warping, which are 2 geometric features that are quite similar to LCS and edit distance, but relies more on geometry, and these two do not appear in the textbook. And I'll talk for quite a while about each one of these four, but when it will get to the code, you'll see that the code is almost the same and the principles are almost the same. So once we understood this part, these three will come very, very naturally. Questions? It's not, we are over time, and yeah, various office hours today at the evening and tomorrow. Thanks, everybody. Sure. I'll have to check what I wrote. I don't remember if I thought that I arranged it so you will. Let me look at it. I thought that I arranged it so you do have one, and then you and it leaves us time to talk about the solutions. But I'm not entirely sure. And so yeah. Let me get back to it. If I do, then I thought that it's questions that I think that are relevant to the midterm. Now, we did not, in the midterm, we will have Bellman-Ford. So I it, if I will not have homework 4, then I'll just give you practice questions. So I mean, I might be wrong, but I think that I mean, I did not make up my mind, but with COVID, etc. I think that the material for the midterm will be everything about graphs, including Bellman-Ford, but and probably will not include the dynamic programming. But I might change my mind. Let me look at it more closely. Midterm, 9:30 Tucson time. I didn't get any complaint about the time, so it's fine with. I'll assume that it's fine with everybody, and yeah. If you can come and do it at the university, it's best. Then we have best communication. I can answer questions. Otherwise, it will be via Examity or without Examity. But yeah, I'll do some head counts when we'll get closer. Yes, and I hope that it's not too late. I should have started it before I went down, but I think, yeah, I'll double check. You need to install something that will make sure that you are not running other things at the same time on your computer. Have you taken an exam on Examity recently? So you'd like to prepare at least 10 minutes to a that they want to validate that you are you and not somebody else. Yeah, yeah, that there is authentication that you are the right person. Now they also want to check, assume that they, at the same time that I used Examity last time, which they want you to take the computer and maybe show your environment. Or alternatively, I'll ask you to have a little mirror, handheld mirror, and show your environment. It might be much easier. And that you don't have. And then they will record you when you take the exam, and what I'm getting at the end of the exam is videos of all of you taking your exam plus warning signs that their algorithms or humans or whoever thought that are warning signs, like you were not gazing at the screen itself. So I'll figure out the details today. The way it looks right now is that you will be allowed to have one file of uh, a, one PDF on your screen, and you'll type your answers. Not optimal. I'd like to allows handwriting, but then I think that it's leaves too many openings for cheating, and so it would be probably typing only. You will be allowed one equivalent of uh, short notes, like 2 pages or 4 pages of handwritten notes that I'll ask you to scan. And I think, and yeah, and probably use D2L. D2L ask you to upload the file after that. I think that Examity allows you to use Chrome, and it's just it will prevent you from run other things. But I think that Chrome slash Safari, it's cool with this. And there is record of everything that you did and record of you while taking the exam. And realistically, it's just how I cannot realistically how we want to create to make it somehow hard and somehow risky for other people to cheat. There is a level of am I sure that it will not happen? No, but uh, you know, it should be extremely important for you to cheat if you want to risk your degree for cheating in the exam, and it's just to make the consequence and the likelihood of getting caught high enough to yeah. And I don't enjoy playing the bad cop in this part. It's not, but it's I think that unfair. It's not that it personally happens to me, but I think that it's so unfair for the students that are struggling with their teeth to succeed honestly, and it's somehow unfair that if you are doing your best by yourself, then you'll get 90. If you are don't do anything, then you'll get 100. Something here is yeah. Yeah. So all the answers, including what's the scope of homework for, practice question, etc. Absolutely, we'll probably have more meetings if we want. So meeting, if you guys want to form groups without me, that's fine. If you want a study group without me, it's fine. If you want to form study group and let me know, and I'll join if I could, or I'll be happy. Of course. Hope that Amir is the same. Yeah. It was all nicely scheduled as nicely as I can get scheduled at the beginning of the course. So you're supposed to cover the material, submit the homework, and maybe even get either the solution or feedback on the homework, everything that is relevant for the midterm. Yeah, I didn't plan for the COVID. So it was supposed to be perfect timing. Uh, so I'll just have to readjust it, or maybe readjust the material. It's not a big deal to decide that Bellman-Ford will not be in the material or not. Don't forget about DAGs that are in the material, and there is plenty and plenty of questions that I can ask about DAGs that has not related to Bellman-Ford, Kuhn algorithm and discovering cycles in DAGs. It's quite there in the materials. Don't forget the median selection and quick sort. That is also lectures that I stuck from last class that are definitely in the materials. Okay, and we can talk more about homework too on Monday. By all means, bye.